Let's start with Azure Storage. This is a managed PaaS offering, meaning we don't need to care about the infrastructure. So that's one of the serverless checkboxes already checked. Scaling-wise, storage accounts scale out of the box. But depending on the type of your account, the scale targets are different. You're looking at those targets right now. You can find them via the link on screen if needed. For most scenarios, Microsoft advises to use a GPv2 storage account, that's General Purpose v2, instead of the older General Purpose v1 account or blob storage account type. On the overview blade of our storage account, we can see that that's the account kind we already selected when we created this storage account in the Getting Started course. In case you do reach one of these limits, you'll start seeing 503 or 500 error codes, server busy or operation timed out. If that happens, you can request a quota increase via the quotas page. You can find that quotas page by searching for quotas in the general search box here. Here you can view all your quotas for the different Azure services you may have. Storage, for example. However, before you do that, I would advise you to consider other approaches. Have a look at your application design. Do you really need all those transactions and bandwidth you're currently using? To save on bandwidth, you could consider compressing the data before sending it. You could also reconsider the retry policy you're currently using. Instead of retrying every second when the server is busy or the operation timed out, retry a failed request after 5, 10, 30 seconds and then stop. And of course, you can always consider splitting up your data. Does all of it really need to be in the same storage account? The limits apply per storage account and not across storage accounts. There's many things you can do here if needed. It would lead us a bit too far to dive into all of these in detail, but via the link on screen you can find a great article that describes some of the approaches you can take to improve this. It lists best practices for performance and stability with blob storage, including the trade-offs. Alright, so this does mean that we can check off the scalability checkbox as well. That's 2 out of 3. The last one we have was the pay-as-you-go model. Let me open the configuration blade of my storage account. There's a link here that points to the pricing model. As you can see, data storage prices are pay-as-you-go, with the option to buy reserved capacity for a lower price. Next to the storing of the data, you also have to pay for the number of operations and the data transfer, but this too is pay-as-you-go. The common things you'd do with a storage account thus fit in the serverless model. In a serverless system architecture, a very typical thing to do is to let something that happens on your storage, say on blob storage, serve as the trigger for something else. I've mentioned it before. When we currently update a blob storage image, a message is put on the queue. That message can then potentially be picked up by something else to effectively execute what needs to be done to handle the message. During the course, we will look into a few ways to improve on this. From letting the blob event itself, so the fact that something is changed or created, serve as a trigger for a function or a logic app, to improving reliability of all of that by putting in Event Grid. More on those scenarios later. So, our storage account nicely fits in a serverless architecture. Up next was Azure SQL. This too is a platform as a service in the way we are using it. So as far as the infrastructure is concerned, we're good. As far as the other two things to check, automatic scaling and pay-as-you-go pricing, there's a specific serverless compute tier for Azure SQL databases we can use. Let's open our SQL database and let's go to the compute and storage blade here. The current service tier I have selected is Basic. This is part of a DTU-based pricing model. DTU stands for Database Transaction Unit. Serverless, however, is only supported by the vCore purchasing model, so one of these here. It's also only available in the general purpose and hyperscale service tiers. If I select one of those, I can see the serverless compute tier appear. This tier does a few things. One, it's a tier at database level that automatically scales based on the demanded workload. Two, it bills you per second of the used amount of compute. So we've got scaling and we've got pay as you go. And as an extra, if you use the general purpose service tier, which we are, it also automatically pauses your database during inactive periods, which makes it even more cost efficient. If I scroll down a bit, I can see that this is actually configurable. This makes this tier very well suited if you've got unpredictable usage patterns, or if you know that you'll have periods of inactivity, like at night. There are trade-offs, however. There is a potential performance hit when returning from a paused state, so be careful with what you choose here. I'm going to switch to the serverless approach for the general purpose service tier. So let me click apply here. And that's happening in the background. That makes 2 out of 3. The last one was the app service that is currently the host of our API endpoints. So let me go back to the resource group and select the app service here. Infrastructure-wise, this again is a PaaS resource, so we don't need to worry about that. As you learned, and we did in the Getting Started course, it can also be configured for automated scaling. So that's 2 checkboxes out of 3. That leaves us with consumption-based pricing. And that is not something that is available for an app service. On the overview blade here, you can see that this app service is linked to an app service plan, and pricing is tied to the app service plan. Let me click through to that. The currently selected pricing plan is B1. When I click it, I can change the pricing plan. But as you can see here, all these pricing plans are built as a cost per hour. So this is not consumption-based. However, what is possible is moving the actual work that is going on inside of the codebase, in other words, the thing that we need CPU cores and memory for, to an Azure function, which is inherently serverless. For example, the code that is inside of an API endpoint handler or the full API endpoint itself can be moved to an Azure function. Or, if one of the parts of your system is a client-facing web app, let that web app integrate with API endpoints that are full-on Azure functions. So, app services are used in serverless architectures, but typically purely for user interaction and or as a very thin layer linked to something else like an Azure function. Switching an endpoint from our app service to an Azure function would thus be a nice demo, and that is coming up in the next section. For now, it's time for this section's summary. So, serverless computing is a game changer. It allows us to concentrate on writing code while Azure handles the infrastructure. The key benefits include reduced operational overhead, cost efficiency, and automatic scalability. You can use serverless computing for various scenarios, like API or function calls, application hosting, workflow creation, API gateways, and so on. Azure offers several services that support serverless computing, such as Azure Functions, Azure Logic Apps, Azure API Management, managed data stores like Azure SQL and Azure Storage, and more. While serverless computing is closely tied to Azure's Platform as a Service or PaaS offering, it also includes additional key features. Automated scaling and consumption-based pricing models are the most important ones. We also discussed the differences between traditional and serverless architectures, weighing the pros and cons of each. Ultimately, as is often the case, the choice between these approaches depends on your specific business needs and use cases. In the next section, we will dive into Azure Functions. Azure Functions is one of Microsoft's most popular Azure serverless services. In this section, we will dive into this. You will first learn what they are, what types exist, and how they can be hosted. Then you will learn how to develop, architect, and publish an Azure function, including how to deal with function app settings. There's also an important part on securing functions, from a security approach between the outside and the function to another approach between the function and the underlying database. Whether you're still developing a function or it's already live, being able to test and monitor them is essential. You will learn how to do that as well. Then you will learn about durable functions. This is a feature of the Azure Functions service that enables stateful functions with a longer execution time, which means they support complex orchestration patterns and can be used for tasks that require state management and coordinating multiple functions. We'll implement one, and of course we will also look at securing and monitoring a durable function. Let's dive in. An Azure Function app is one of Microsoft's serverless services. That means that the infrastructure is managed for you, automated scaling is possible, and pricing can be consumption-based, which is typically cheaper. So you can focus on writing code and let the Azure Function app service handle the rest. Just as with a lot of Azure services, you can choose from different programming languages to develop in, like Java, JavaScript, Python, but also of course C#, and that's what we will use. Many potential scenarios are supported for Azure Functions. Think about a function that cleans up some data from your database every hour. A function that processes an image blob whenever a new image blob is added to one of your storage containers. A function that listens to storage queue changes to trigger additional message systems, or even processing of whatever is put on that queue via an OpenAPI service. Or maybe a function that serves as a web API endpoint, triggered when a certain HTTP request comes in. There is of course overlap with other Azure services. You can create web API endpoints on an app service as well. And you can create workflows with logic apps, as we'll see in the next section. It's not because you can do something with an Azure function that is the right approach. But if you need auto-scaling and pay-as-you-go pricing, Azure functions are a very good option and are worth considering. All of this is enabled by two fundamental concepts of functions: triggers and bindings. A trigger is what causes a function to run, and each function must have exactly one trigger. Triggers define how a function is invoked, and often include associated data that is sent to the function. A few examples are an HTTP trigger, for example, one which would cause a function to run when an HTTP GET request is sent to a URI. A timer trigger, which causes a function to run on a scheduled time. Or a queue trigger, which causes a function to run when a message is put on an Azure storage queue. And that seamlessly brings me to bindings. A binding is a way to declaratively connect a function to another Azure resource, like for example that storage queue. Bindings can be input bindings, which provide data from another Azure service to the function. Output bindings, which enable a function to, for example, write something to a storage queue or an Azure SQL database, or both. Two types of Azure functions exist: regular functions and durable functions. A regular function is designed for short-lived, stateless operations and is typically event-driven. Processing an HTTP request, handling a message from a queue, executing some simple logic when a blob has changed. Stuff like that is very well suited for that approach. A durable function is an extension of, or a feature of, if you wish, Azure Functions that enables you to write stateful functions with a longer execution time. Thanks to that, it supports complex orchestration patterns and can be used for tasks that require state management and coordinating multiple functions. Examples are workflows that take up some time, or a process that needs to wait for human input. If you compare these two, you get the table that you see on screen now. And with that, you should have a good idea of what functions are and which scenarios they enable. Time to create one.